So the problem that has been given to you consists of a column of gas. There is constant uniform gravitational field G, and there is some reference height h. This is height h equals to 0. So everything is measured with respect to this reference height, and the main thing that has been stated is the fact that the temperature T is held constant. The temperature is held constant, which is of course very unlikely because there is something called lapse rate, and the temperature as you go up falls in atmosphere at least. The second assumption is that the gas that is here is an ideal gas, so it obeys PV equals to N, so let us just write it, PV equals to N number of moles RT, which is also the same as saying that P equals to N KT NKT, where N is now the number density. This is the number density. Here it is written in terms of number of moles, here it is written in terms of the actual number density of particles. So this gas follows this ideal gas equation of state, and the question that has been asked is how does the number density vary with height. So the question is how does this number density vary with height. This is the question. So these are the things that are given. T is held constant to some value T, and this ideal gas equation is there, and you are asked to find N as a function of H. So what you essentially have to do is consider these two levels at some height h and h plus delta h. The pressure here is P h plus delta h, here the pressure is P, and you can immediately see from using your notion of pressure in fluids that the change in pressure across this thickness, which you can write as delta P, equals to minus rho g delta h. Now why is this minus sign coming from? The minus sign is because of the fact that height is increasing this way, whereas the pressure here is less than the pressure here, so clearly there is a minus sign. Great. Now this is one thing that you have, and then you of course have pressure equals to NKT. So from here you can just see that delta P equals to delta N KT. T is constant, so that is why we could just differentiate the N. And then if you equate these two, from these two you have a simple differential equation in the limit that the delta goes to a differential. So you have dP equals to dN KT equals to minus rho g dH. Now this rho, which is the density of the gas, is basically the mass of each molecule times the number density. So here you have minus mg n dH, and thereby you have dN by n equals to minus mg gh. And the integration of this is very simple, so integrate both sides, and what you have is logarithm of n equals to minus mg h. Of course there is by kt, to take the dn by n equals to kt has to go to the other side, so you have mgh by kt. So log n equals to minus mgh by kt, which immediately means that n equals to n at h, and that is equals to n at 0 x e to the power minus mgh by kt. Let me write it down over here. We have n at h equals to n at h equals to 0 e to the power minus mgh by kt. It is a very important law that number density essentially falls off exponentially as you go high up. All right? It is quite interesting because there is one more thing I would like to note about this problem. It is the fact that if you consider some reference height 0 say over here and some height h over here, and now consider that there are gas molecules which are moving up and down and with all sorts of velocities, and if you are interested in upward moving molecules, we are just focusing our attention to molecules which are moving upwards. Now, any molecule which has an upward velocity component v over here, do you think it is going to reach here? Clearly not, because it would not have sufficient energy to climb to that height, right. So, if the molecules which are moving with velocity v over here has to reach this height h, you immediately know from conservation of energy that half mv square should be equals to mgh, or v square equals to 2gh. So, for a given velocity v upwards, a molecule can go up to h, satisfying this condition, v square equals to 2gh. Now, the question is, if I start with molecules with speeds v in the vertical direction upwards greater than v, so greater than v, so and with v equals to say 2gh, v square equals to 2gh, then the molecules per unit time, the rate, and this is of course a random thing that is happening, but on an average the rate of molecules, the rate at which the particles are going up here, over here the number density of particles with velocity greater than 0, because when it is greater than v, when it is just equals to v, it will reach here with velocity 0, but here we have put the condition at h equals to 0, I have put this condition greater than v. So, at h equals to h, the molecules will reach with velocity greater than 0, right. So, we can immediately say that number of particles, right, which are moving upwards with rate velocity greater than v at h equals to 0, this must be equals to the number per unit time, this is the rate, number of molecules moving with velocity greater than 0 at h. Very important. Now, look at this. This just tells you how the number densities vary. The number density of molecules would vary as you go from h equals to 0 to h equals to h, but the distribution of molecular velocities, which depends only on the temperature, in the slides you saw the Maxwell-Boltzmann distribution, which depends only on the temperature. So, clearly the distribution of molecular velocities would be same at both the heights, because the temperature at both the heights are held constant. So, since the distribution remains the same, we can immediately say that the number of molecules with some speed greater than some velocity v at h divided by the number density at h, the total number density of all possible molecules. Now, this has all kinds of speeds, and this is some restrictions on the kind of speeds we are interested in, moving upwards with velocity greater than v. Now, this is the distribution, right? It is a ratio of number of particles with some velocity constraint, speed constraint divided by the total. It is like the probability distribution. Now, this we expect to be the same to number greater than v at 0 by the number density at 0. This is the statement saying that the distribution functions are same at the two heights. Okay. Now, we can always choose this velocity to be 0 because it is an identity. So, I can take this and then I use this condition, and the moment I get this, write this condition down, what do I have? This quantity over here is to be replaced by this. So, you could simply write number greater than v at 0 divided by number at h is equals to number greater than 0 at 0 divided by number at 0. So, if you divide this, if you take this to the other side, this is what you would have: number v greater than v by number greater than 0, both at 0, equals to nh by n0, and nh by n0 is given by e to the power minus mgh by kt, but mgh is now related to v square. So, this is a very important result, that this is equals to minus m v square by 2 kt. Number of particles moving with velocity v, upward velocity v and higher at 0 divided by the number density of all particles moving with velocity greater than 0 upwards at 0 is given by this factor. So, both of these forms are quite important. I would urge you to please go through Feynman Lectures chapter 40, where he uses this as an argument to get to the point where he writes down the Maxwell-Boltzmann distribution. We shall not do it in class. There is some subtle nuances, but please have a look at this, and we shall discuss it in the next class. Thank you.